Welcome to our video on De Morgan's theorem. In this video, we will learn how this important rule in Boolean algebra helps us simplify complex logic expressions. We will see how we can turn ands into ors and vice versa just by adding nots in the right places. We will explain each rule with examples, truth tables, and simple logic gate diagrams. By the end of the video, you will understand how De Morgan's theorem makes it easier to design and simplify digital circuits. Let us begin by understanding what Boolean algebra is. Boolean algebra is a branch of mathematics that deals with binary values, true or false, or simply 1 and 0. It uses logic operations to work with these values, making it a powerful tool for analyzing and designing digital systems. Why is it important? Because every digital device, from a calculator to a smartphone, relies on a logic circuits that follow the rules of Boolean algebra. It helps engineers and developers create systems that make decisions, perform calculations, and process information efficiently. Now let us look at the three basic logic operators and returns true only if both inputs are true, or returns true if at least one input is true. Not simplify flips the value, turning true to false and false to true. These basic operators are the building blocks of all complex logic expressions. De Morgan's theorem was introduced by Augustus De Morgan, a British mathematician known for his work in logic and mathematics. This theorem gives us simple but powerful transformation rules for Boolean expressions. It shows how we can switch between and or operations when we apply the not operator in the right way. These rules are especially useful for simplifying logic circuits, making them easier to design, understand, and implement in real-world digital systems. De Morgan's theorem consists of two fundamental rules that allow us to rewrite logical expressions using not and or operations. Let us start with first theorem. Not of A or B is equal to not A and not B. In Boolean terms, we write this as negation of A plus B is equal to negation A dot negation B. This means if the result of A or B is false, then both A and B must be false individually. Now the second theorem says not of A and B is equal to not A or not B, or simply negation of A dot B is equal to negation A plus negation B. In other words, if A and B together are false, then at least one of them must be false. These theorems are essential in simplifying logic circuits and help in converting between NAND and NOR implementations. Let us verify De Morgan's theorem using a truth table. For the first theorem, we compare the columns for negation of A plus B and negation A dot negation B. For the second theorem, we compare negation of A dot B and negation A plus negation B. As we can see in both cases, the outputs in the corresponding columns are identical for all combination of inputs A and B. This confirms that both theorems are logically valid. This slide shows the graphical representation of De Morgan's theorems, which are fundamental in digital logic design. The first theorem states that the complement of the OR of two variables is equal to the AND of their individual complements. The second theorem says that the complement of the AND of two variables is equal to the OR of their individual complements. These theorems are extremely useful in simplifying logic circuits and in converting between AND OR forms and NAND NOR forms. In practical terms, they allow engineers to implement logic with fewer types of gates, which reduces hardware cost and complexity. One of the most important uses of De Morgan's theorem is in logic simplification. It allows us to reduce complex Boolean expressions into simpler forms, making circuits easier to understand and build. This theorem is also helpful when we need to replace NAND or NOR logic with basic gates like AND, OR, and NOT, especially in situations where certain gate types are limited or unavailable. Overall, using De Morgan's theorem leads to simpler, more efficient circuit designs which are easier to implement and often more cost effective. Let us look at an example to apply De Morgan's theorem. We are given the expression not of A or not B. Using De Morgan's first theorem, we can rewrite this as not A and B. This transformation makes the expression easier to implement using basic logic gates and is especially helpful when designing or simplifying digital circuits. Now let us look at some real-world applications of De Morgan's theorem. First, in digital circuit design, this theorem helps engineers simplify logic circuits by reducing the number of gates needed. This leads to faster and most effective systems. Second, in computer architecture, De Morgan's laws are used to optimize control logic and memory access conditions in processors and embedded systems. Finally, in programming and microcontrollers, Boolean expressions often need to be simplified for better performance. De Morgan's theorem makes it easier to rewrite complex conditions into simpler, more efficient logic. These applications show how a basic mathematical rule plays a powerful role in the technology we use every day.